Okay, I think it's recording. Great.
Are we ready to start?
I think we can wait until 9.
Okay.
There were some sponsors will come. You guys probably can change the slide to the display mode. Right now I can see 2 of them. And
Okay. So you're seeing the presenter mode as well?
sorry?
You're seeing the presenter mode?
I don't know what it is. I mean, I should not be able to see 2 slides, right? So.
Okay, I'll try to share again. Give me one moment, please. I'm sorry about that.
Okay, it's okay. Yeah, great.
Good, okay.
So I guess we can start. It's recording, so everything good.
All right, I'll go ahead and start. Hello, everyone, and thank you for joining us today to learn about the belt-equipped solar tracker, also known as the B.E.S.T design. I'm Jose Camacho, and our design team consists of myself, Zaewon Jin, Evan Lynch, Kaylee Porter, Akshay Ramakrishnan, Macaulay Redding, and Samuel Stahl.
Trying to get this slide to change.
So in this presentation, we would first like to introduce you to our hedgehog concept and the inspiration for our design. We will then walk you through the capabilities of the belt-equipped solar tracker heliostat, along with the driving system used to control it. The explanation of the capabilities will then be followed by a few video presentations showing our heliostat in action. We will then conclude the presentation with the overall value of the design and the total cost breakdown, at which point you may ask any questions you have, and we will do our best to answer them. The hedgehog concept for our design was based on designing a product that could reflect light accurately and efficiently while keeping the design as simplistic and affordable as possible.
So what feels like ages ago now, even though it was only like 13 or 14 weeks, this engineering design team was stepping foot in the MAA lab together and essentially was told, here's your group, I hope you like them, and now get to work. So not only were we presented with this information that we were essentially being forced to like each other enough to produce a heliostat prototype, but on the first day of class, we were also thrown with the news that our designs for MEC 2 were not up to par and to try again. So lucky enough for us, we were able to continue this iterative design process with a new set of engineering minds coming together. And I think the end product of our heliostat was pretty successful. But before the success, we went through what is called a house of quality analysis, where we evaluated 4 previous MEC 2 designs that we deemed were promising choices, as well as a baseline model that you can see here on the left. So we took these 5 designs and we compared them against the customer need requirements as well as the design requirements to be able to score them and get down to our final design choice that we thought would be the best. So the baseline model was presented to us on the first day of class as a design that was unique from our previous MEC 2 designs, and it was strongly encouraged for us to evaluate its capabilities further. After sitting down and completing the down selection process within the House of Quality Analysis, the baseline heliostat design was determined to be the best design concept in terms of scoring. However, the group decided to move forward with a modified hybrid design that combines the baseline model and Summer Group 1's model. And lucky enough, one of our members here today was a part of the Summer Group 1 team, so he was able to further explain the design concept to us. So when I say the hybrid model, that is meaning, for example, the enclosed motors in the baseline are combined with the motor positioning and axial movement of Summer Group 1's design. Our group decided to not move forward with the baseline design because of aspects such as implementation of the harmonic drive, overall cost being too high when we initially looked into it, not having quality 3D printed parts, and other examples such as that. And with this short time frame and limited knowledge of the baseline, we decided to move forward with a more feasible, familiar design to us. And then the best features. So with our heliostat design, it has the capability to move the mirror up and down, and the base allows movement of the entire heliostat in a circular motion. The azimuth rotation has full movement in 270 degrees, and there are 180 degrees of rotation for our elevation. This large range of movement allows our heliostat to chase the sun throughout the day, no matter what the position of the sun is in the sky. The way the heliostat is designed allows for our motors and electronics to be safely stored inside of the 3D printed housing. Our design also features a dual supported mirror to allow for reflection back to the central receiving tower. And lastly, the housing for our motors, electronics, and other components features cooling vents to prevent the internal parts from getting overheated. In the following slides, we will address these features in more detail.
The motor housing, also known as the main body, encases the motor, electronics, and belt drive systems. The entire motor housing was printed using PETG material with sufficient thickness to support the various attachment points and withstand the elements from the environment. The front panel of the motor housing removes completely using 10 screws, which gives the user easy access to all of the internal components when maintenance is necessary. Because of the confined space for both NEMA stepper motors, a ventilation port with 4 slits was incorporated on the front panel to reduce thermal buildup within the motor housing. The total area of open ventilation is 13.88 centimeters squared. Heat calculations were necessary to ensure that the interior of the motor housing would stay below the maximum working temperature for the NEMA stepper motors, which was a value of 212 degrees. Using the resistance and the current from both motors, the input power could be calculated. The surface area for the walls of the motor enclosure that doubled as exterior walls of the motor housing were then calculated. By dividing the power by the square footage of surface area, the input power was found to be 17.9 watts per square foot. Using the chart in the upper right-hand corner, the temperature rise could be up to 60 degrees Fahrenheit. Using an extreme recorded temperature for the United States of 134 degrees Fahrenheit, the temperature could potentially rise to 91% of the maximum working temperature of the stepper motors. This calculation led to the implementation of ventilation on the front panel of the motor housing.
The mirror in the heliostat was 6 by 9 inches and 1 millimeter thick and was attached to the mirror mount with adhesive backing. The base of the heliostat is 3D printed using a sturdy PETG material and was snap fit into an aluminum quick release camera mount. This camera mount provides a double lock, so the heliostat was safely locked in. The driving system in the heliostat incorporated the use of two NEMA 17 stepper motors that were already given to us in class, and these were used to achieve uniaxial rotation. The two identical step belt drives were created to facilitate the motion of the heliostat. These drives are shown in the picture on the bottom and the left-hand portion. Each belt system achieved a 5-to-1 output to motor torque, and in combination, it was a 25-to-1 output to motor torque. One of the design constraints in the baseline design presented to us was solving backlash in the system due to the harmonic gear drive. To accomplish this, our group shifted to a belt system to avoid dead spots when changing direction, because in this case, the T-tier won't slip. This effectively made our system experience minimal to no backlash.
The reduction of the motor torque to the output torque occurs through a two-stage reduction, with each stage using 16 and 80 tooth pulleys for a 1:5 ratio. Stage 1 utilizes a GT2 neoprene belt, and due to the higher torque on stage 2, 2 belts were necessary. What allows this system to work is the system of tensioner screws, which move the intermediate gears closer and further from the input and output gears. This allows for easy removal and insertion of the belts when necessary and proper tensioning for use. The electronics of the system is controlled using the ESP-WRoom32 microcontroller designed for Arduino. Because this controller only outputs a maximum of 5 volts, a 12-volt DC power supply was needed to drive the NEMA 17 stepper motors. This was done through the use of an A4988 driver. 4 micro limit switches were also incorporated to help set the home position of the heliostat, as well as protect the module from over-rotation by setting maximum and minimum points of rotation. Enclosure temperature data is also available via the SHTC3 digital temperature and humidity sensor. These electronics allow for the functionality of the heliostat to incorporate all of the design requirements. First, it is able to set azimuth and elevation angles through user-defined inputs, as well as move a user-specified angle or number of steps in either axis. Our reduction allows for an accuracy of 72 thousandths of a degree based on the reduction and the step size of the motors. This, coupled with the 5% accuracy of step through the motors, allows for high precision when tracking the sun throughout the day. Another capability of the heliostat is to assume the home and safety positions. This is important for ensuring damage does not occur in high wind settings. Lastly, a function of the heliostat is to output the enclosure and motor temperature to prevent overheating. These functions are carried out through the command language given to us. This operation is essential to meeting the customer requirement of commands coming from the central computer and input data being fed back to the computer for solar tracking.
So one of the first assessments conducted during the prototyping phase was the wind survivability test. And the goal of this test was to demonstrate that our heliostat system was robust against the most extreme weather conditions possible at the Las Vegas, Nevada target installation site. The testing involved 2 configurations of the heliostat, a normal mode and a safety mode, and 2 speed settings of the fan, which was a low speed simulating around 5.3 meters per second or 12 miles per hour wind, and a high speed setting of 60 meters per second or 134 mile per hour winds. The normal mode configuration had the heliostat set up in a vertical position or position with the highest drag coefficient, and it was only used for the low speed test. The safety mode configuration had the heliostat mirror position parallel to the ground at the position of the lowest possible drag coefficient, and this was only used for the high speed test. So for the low speed assessment, it involved 2 tests. The first test was the heliostat was positioned in the normal mode, and the fan was set on a low speed of 4.3 meters per second, and our heliostat was inside the wind tunnel for 5 minutes, subjected to those conditions. For the second test, the heliostat remained in the same normal operation mode position, but the fan was then set on a speed of 5.3 meters per second. Again, the heliostat remained inside the wind tunnel for 5 minutes or 15 full rotations. Now for the high speed test, this assessment also involved 2 tests, and the fan was switched out for a blower to simulate the higher speed wind conditions. For the first high speed test, the blower was set on a low speed of 60 meters per second, and their heliostat was subjected to the wind conditions for 5 minutes or again 15 rotations. For the final test and the second high speed test, the blower was set on high to 88 meters per second, and the heliostat was subjected to these conditions of wind speed for 5 minutes or 15 full rotations again. So on the left here is the fan, which is the low speed test, and the right was the high speed test. But yeah, we can play the video. So this video is a portion from the high speed test. This specific snippet is when we were simulating the 60 meter per second wind speed or 134 miles per hour on the safety setting mode or the safety mode setting. And so as you can see, we can play the video again. As you can see, like when our heliostat was rotating, it was withstanding the wind force from all angles. And so this test proved that the heliostat would withstand the most extreme wind conditions that would be possible on the site. And so overall, outside of that, our heliostat here proved that the aerodynamics could work for the final design. It was able to be configured in a normal operation mode and a safety mode. It survived the low speed test at a normal operation mode, and it survived the high speed test at a safety mode. And all these combined allowed us to receive a full 20 out of 20 points on the wind survivability test.
Good morning. My name is Evan Lynch, and I have been focused on performing calculations related to environmental factors and developing a kinematic model of our heliostat. We performed wind calculations to ensure our heliostat would meet the customer requirement of a minimum factor of safety of 2 on all parts. We estimated the wind force as a drag force using a coefficient of drag of 1.98. In the safety position with the mirror and body facing parallel to the wind direction, this resulted in a force of 188 newtons. The part under the most stress was the azimuth output shaft. This part was constructed of PETG, which had a yield stress of 46 MPa. The stress at the output shaft was 23 MPa, resulting in a factor of safety of 2. Similarly, a wind calculation was performed in operating position. This is with the mirror and body facing perpendicular to the wind direction. At 54 meters per second or 121 miles per hour, this resulted in a force of 221 newtons. This resulted in a similar bending stress of 23 MPa at the azimuth output shaft. For the laser test, a kinematic model was needed because we have eccentricities about both axes of rotation. This means the position of the mirror changes relative to the origin, with rotation in azimuth and elevation directions. Our kinematics resulted in a system of equations with 2 unknowns because the target position is dependent on the mirror's final position. Arduino IDE is not capable of solving a system of equations, so MATLAB was required. This appeals to the customer's expectation that a more powerful central computer would perform the calculations. The laser reflection test was designed to prove that our heliostat and kinematic model was capable of meeting the customer requirements. The 2 customer requirements that relate to this test are less than 0.5 degrees of tracking error and the ability to reflect light onto a tower up to 100 meters tall. During this test, the sun was modeled as a laser beam pointed vertically down onto the mirror. Using trigonometry, the plus or minus 0.5 degrees tracking error was converted into a circular target and posted around the room. This is depicted as the yellow region in the diagram, which is approximately 4 meters away from the heliostat. The first part of the test demonstrated we could accurately reflect light onto a target provided its coordinates. Another target was used to demonstrate we could solve for the Cartesian location of a target using manual control. The fifth and last target was posted on the ceiling, and we were not provided coordinates until right before the test. Furthermore, our heliostat had to respond to serial input and report temperature, move to danger position, and power down to successfully pass the laser test. Next slide, please. This slide shows a video of our heliostat reflecting the laser during a practice session. We were the first group to attempt and pass the laser reflection test. We were able to successfully hit 4 targets with less than 0.5 degrees of error. The last target was achieved with an error of less than 1 degree. The 1 degree of error could be easily reduced by calibrating the heliostat with targets in multiple planes rather than one. This resulted in a score of 49 out of 50 possible points for the laser reflection test. Next slide, please. Now I'd like to welcome Kaylee to present the cost breakdown.
Thank you. So now for the part that you may all care about the most, the price to create this heliostat prototype. So the design you've been presented in the form of CAD models, videos, and pictures on the previous slides comes out to a total of $155. So this price factors in the cost of our printing filament for our 3D printed parts. And I'd like to note that our 3D printed parts made up about 15% of our total cost, and the remainder of the cost came from over-the-shelf parts such as pulleys, belts, motors, and motor drives. And now for the even bigger number. So we did a cost breakdown for 3,000 heliostats, which is a more realistic number for what we would be using out in the Las Vegas desert or a similar area. So the price that we got for this amount was around $451,000. And we were able to save money on the stepper motors by increasing the total quantity ordered. However, the pricing per unit remained the same for every other part ordered or 3D printed. This price is strictly based on the same exact parts that we used for the prototype heliostat. So it would be important to do more investigation into other alternative parts that we could be using that would perform the same way as the parts in our heliostat prototype. Additionally, I would like to also see communication with the manufacturers for the OTS parts in order to see if we could have some kind of special pricing done given the quantity that we would be ordering.
So like Kaylee said, considering that all our parts are 3D printed, excluding the interior electronics, the belts and screws, it provides accuracy and it provides affordability in addition to accuracy directed at solar-driven companies. So essentially, cheaper 3D printed parts will provide major savings while still providing quality and meeting the customer needs. The fact that our design uses a belt-driven system provides for the uniqueness of it, and the fact that it's quiet and a belt-driven system has zero backlash. Another reason for our design is the fact that it uses a one-piece enclosure, which provides for the simplicity, and our 1:25 gear ratio provides for the accuracy, and that was seen before where we reached an error of less than half a degree. All in all, we want to thank you for listening to our presentation. We're the B.E.S.T heliostat team, and we'll now open the floor up to any questions you guys may have. Thank you.
Thank you for the presentation. Great job, everyone. So any questions from our audience?
Yeah, I'll go ahead and start. If you wouldn't mind going back to the costs, please. Perfect. Okay, so actually go to the 3,000 costs. That will probably make a little bit more sense. Perfect. Okay. So I notice a lot of, let me take a step back. I'm not an engineer. So please first excuse any of my, thingamajigs and whatchamabobs when I call it this stuff. Okay. So y'all got a lot of stuff here. What I don't see accounted for is manufacturing labor or assembly labor. Can you speak on that a little bit?
Yes, I'll speak on that. So the primary design requirements that we were given were for the production of the heliostat itself in materials, and that's where the cost came from for the single prototype slide that you saw before. And as Kaylee mentioned, this cost analysis for the 3,000 heliostats was more of a analysis of the materials and everything that would go into the heliostats, and a manufacturing cost was not accounted for. But in actual practice, that is something that would need to be accounted for in the production of.
Yeah, because if I take the view of an investor, like, ooh, do I want to buy, your heliostat because it's the best? I like the name, very cute. So this doesn't really represent a true number. If you come to me and say, hey, it's going to cost you 451,000. And when I hand over that check, either y'all are going to be out a lot of money because now you've got to figure out assembly costs, because if you just hand me 4x20 dowels, I'm going to probably use it as a fetch stick with my dog, because I wouldn't have any idea what to do with it. So that's something you definitely need to take into consideration, because labor costs get kind of expensive, especially with how many parts and bits and pieces y'all have. You're really going to need to be considering those. It's not going to be your most expensive cost, but it is going to add a bit of money to this. So just, kind of take that in consideration moving forward. Totally left field, something else is I want to thank y'all for the ones that dressed up, that, look professional, that look really nice. That definitely helps put some faith in investing in your product. When I see that y'all are trying to look professional and act professional, it makes, me think you are professional. So thank you for that. The one last thing, I'm really bad at like the Oreo, the good, bad, good. So please, sorry. In the presentation, look, I know y'all were kind of just thrown into a group and, things were not perfect. Welcome to the real world. When I get a job, I don't get a choice in any of my coworkers. And believe me, I really wish I did. So in this presentation, you may not want to harp on the negatives so much. We all know, yeah, situation kind of sucked. We all know, oh, probably wasn't the, when you went into the testing, things weren't great. But when you start kind of throwing out negativities like that, it really affects me as an investor, like, oh, I feel negative too. And the last thing you want is an investor to feel negative. You want me to come out of here skipping with joy, eating a lollipop. So those are little tiddly-wat things, they're very little, so don't like cry over spilt milk, but definitely kind of be aware of that stuff. But other than that, for the little bit of engineering I understood, very good presentation.
Thank you very much, Julia.
Thank you. So since okay, so I have 2 minutes left. So could you please go back to, well, there's no page number, so make sure that in future when you do presentation, always have page number. It's really hard for me to track, like, so I believe on one page you said you have like 4 opening for ventilation, and at the beginning, and it's like the area is 13.88. I don't know. Yes. So I see you list this 4 openings, total area of 31. And it's my question is, did you do any analysis on this? When you list this number here, it is enough, or it's based on some kind of calculation, or it's just your design you showed here?
So for the calculations that we performed, it was more on seeing how much thermal buildup would occur from 2 motors in the housing directly.
Yeah.
We did not calculate as much on how the amount of area that we implemented would affect that heat transfer.
So this 4 openings and total area of 30.88, just your design.
Yes.
Okay. So I just want to, well, overall great job and congratulations on the successful on the reflecting test. That's amazing. But from the presentation as engineer, I would prefer more analysis. So let's say you said, okay, we have motors and how much heat it will generate, and you can have a rough estimation that how much heat our ventilation system or thermal control system need to handle. And then we talk about, okay, for this much heat, how do you want to design a thermal control system? Let's say you use a ventilation system, something, how large of the total area is required? Then I know that, okay, if this 13.88 is enough or it's too much, right? It's not just show our design. Our goal as engineering students is that we need to present our design that based on our analysis, our design is the best because it's optimized on everything. It's not just show, okay, we have 4 openings, we have 13.8. And the wind survivability test. Could you please change the slides? Yeah. Yeah, so yeah, next slide. I want to see the analysis part. Next one. Yes. So and I feel a little confusion here because here you use Vmax as 88 in your calculation, but during your test, you use 5.3 and 60 for different mode. So why there is a difference in calculation and in your test?
So for like the test, for the high-speed test, there are 2 different versions. There was like, so for high speed, there was a low speed of 60 meters per second. And then there was a second test, which was like high. And so that was the one that was at 88 meters per second. So we just used that for the wind force, like just the max wind force.
Okay. So in the test, you did the 88, but you didn't put it in the slides.
No, that's what we said for like, that's what we mentioned the slide, like 2 slides before, and then we used it here for the wind force.
2 slides before, you mentioned that one mode is 5.3, one mode is 60. You can go back, check that slide.
Yeah, it says, so yeah, like you're correct. It says 60 there. Like we just said that because in the slide after, that specific test is also like 60 meters per second.
Yeah.
So we figured we just, continue that.
Yeah, that's why I'm asking why in the test is 60, but in your calculation is 88.
Wait, like, so like,
the calculations on these 2 slides are the max theoretical speeds that the heliostat could survive with a factor of safety of 2. It was tested to 60 meters per second, but it should survive 88 meters per second without failure.
Then does it mean that your test didn't approve your safety factor 2? That's my understanding, right? Because if you want to approve that you have safety factor 2, you need to use the speed 88, but you test at 60. Am I correct, or I misunderstood it?
60 meters per second is the extreme condition for Las Vegas that meets the customer requirement. This slide just shows that our design could be implemented elsewhere in higher wind speeds than just Las Vegas.
Okay, 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 okay. Thank you. The output shaft bending stress, the material is 46, and what is this 23 megapascal?
23 is the bending stress.
Is the actual stress in your material?
Yes.
During the wind test? Do you have any calculation related to this?
Not shown on the slide.
Because for me as an engineer, I feel a little surprised when I see that you use a material with yield strength 46 megapascal, and now you perfectly calculated your maximum stress at 23 megapascal with safety factor 2. I'm really surprised at this result. So if I see something like this, wow, it's perfectly 23, 46, material property is 46, your maximum stress is 23, and your safety factor is 2. Everything is perfect. I mean, I want to see some calculation to show me. That's my feeling. You cannot just tell me it's 23. I need to see your calculation. What caused this 23? And also, I feel like, again, as senior design in mechanical engineering, I do want to see some structure analysis, but I don't see any here in your presentation. Yeah, and I think that's all my comment. I think overall your group did a great job on making the whole thing and pass all the tests successfully. Just in the presentation, we probably want to see more analysis as senior engineer students. It's not a show your design. We want to know why you design this way. How do you prove that your design is best, right? If you don't show me the analysis to show you that your analysis is the best, is optimized on everything, I'm not convinced. So that's what I mean. So overall, congratulations and great job. Thank you.
Thanks.